AC current mirrors. Figure illustrates two examples where a current source proves useful. From our study in chapter, recall that the output resistance and capacitance and the voltage headroom of a current source trade with the magnitude of the output current. In addition to these issues, several other aspects of current sources are important: supply, process, and temperature dependence, output noise current, and matching with other current sources. We postpone noise and matching considerations to chapters respectively. How should a MOSFET be biased so as to operate a stable current source? To gain a better view of the issues, let us consider the simple resistive bias shown in figure. Assuming M1 is in saturation, we can write I out similar to 1 by 2 nu n C naught x W by L into R2 by R1 plus R2 VDD minus VTH whole square. This expression reveals various dependencies of I out upon the supply, process, and temperature. The overdrive voltage is a function of VDD and VTH. The threshold voltage may. Here you can see application of current sources. Here you can see the figure definition of current by resistive divider. Vary by 100 millivolts from wafer to wafer. Furthermore, nu n and VTH as bit temperature dependence. As I out is poorly defined, the issue becomes more severe as the device is biased with a smaller overdrive voltage, that is example to consume less headroom. With a nominal overdrive of say 200 millivolts, a 50 millivolts error in the VTH results in a 44% error in the output current. It is important to note that the above process and temperature dependencies exists even if the gate voltage is not a function of the supply voltage. In other words, if the gate source voltage of MOSFET is precisely defined, then its current then its drain current is not. For this reason, we must seek other methods of biasing MOS current sources. The design of current sources in analog circuits is based on copying currents from a reference with the assumption that one precisely defined current source is already available. While this method may appear to entail an endless cycle, it is carried out as illustrated in figure. A relatively complex circuit, sometimes requiring external adjustments, is used. Here you can see the figure, use of reference to generate various currents. To generate a stable reference current IREF, which is then copied to many current sources in the system. We study the copying operation here and the reference generator circuit in chapter. How do we generate copies of a reference current? For example, in figure we do. How do we guarantee I out equal to I reference for I reference for a MOSFET if ID is equals to F of VGS, where F of dot denotes the. Here you can see the figure conceptual means of copying currents. Functionality of ID. versus VGS, then VGS is equals to f of minus 1 of ID, that is if a transistor is biased at IR reference, then it produces VGS equals to f of minus 1 f of minus 1 of I reference mod figure A, as if voltage is applied to the gate and source terminals of a second MOSFET. The resulting current is I out is equals to f of f power minus 1 I reference f of minus 1 of I reference is equals to I reference into figure B. From another point of view, two identical MOS devices have equal gate source voltages and operate in saturation, carry equal currents if lambda equals 0. Figure A, diode connected device providing inverse function. B, a basic current mirror. The structure consisting of M1 and M2 in figure B is called a current mirror. In the general case, the devices need not be identical. Neglecting channel length modulation, we can write I reference equal to 1 by 2 nu n C naught x W by L1 into V of Gx minus V Th whole square. I out is equal to 1 by 2 nu n C naught x into W by L2 into VGS minus VTH whole square. Obtaining I out is equal to W by L2 by W by L1 I reference. The key property of this topology is that it allows precise copying of the current with no dependence on process and temperature. The ratio of I out and I reference is given by the ratio of device dimensions, a quantity that can be controlled with a reasonable accuracy. Current mirrors find wide application in analog circuits. Figure illustrates a typical case where a differential pair is biased by means of a NMOS mirror for the tail current source and a PMOS mirror for the tail current for the load current sources. The device dimensions shown establish a, here you can see the figure current mirrors used to bias a differential amplifier. Drain current of 0.4 IT in M5 and M6, reducing the drain current of M3 and M4 and hence increasing the gain. Current mirrors usually employ the same length for all of the transistors so as to minimize errors due to the side diffusion of the source and the drain areas LD. For example, in figure, the NMOS current sources must have the same channel length as M0. This is because if LRON is say doubled, then L efficient is equals to LRON minus 2 LD is not. Furthermore, the threshold voltage of short circuit devices has bit some dependence on the channel length chapter. Thus, current ratioing is achieved by only scaling the width of transistors. We should also mention that current mirrors can process signals as well. In figure B, for example, I reference increases by delta I, then I out increases by delta I, W by L2 by W by L1. That is, the current amplifies the small signal current if W by L2 by W L1 is greater than 1, but at the cost of proportional multiplication of the bias current. Thank you.